this session. I'm pleased to introduce Maria Khalusova. Maria is a developer advocate at JetBrains, where she focuses on data science and machine learning. She also blogs, presents at conferences, and runs PyData Montreal meetups. She will be presenting a talk titled A Closer Look, Exploratory Data Analysis with Spark and IntelliJ IDEA. Please join me in welcoming Maria.
Thank you. Can you hear me? Yes, perfect. My name is Maria Khalusova. Thank you so much for coming to my talk. I work as a developer advocate at JetBrains, and today I'm going to do a little bit of exploratory data analysis with Spark and with a twist that I'm going to be using IntelliJ IDEA for that. And at the end of after the talk, I'm going to be sharing the slides and a GitHub repo with a notebook with the code. And if that's something you'd like to look at, here's my Twitter handle. It's my name without spaces, and there you can find the links. Also, if you have any questions during the talk, feel free to tweet them at me so that you don't have to remember them until the end of the talk. All right. A little bit about me. I'm primarily a Python person. My normal tooling is Jupyter, PyCharm, the pretty standard set of libraries, pandas, scikit-learn, NumPy, all those things and more. And occasionally I also do Spark. And when I do Spark, my preferred notebooks are typically Apache Sapling. And sometimes I use PySpark, sometimes I use Scala. New functionality in the Spark world tends to come first in Scala and then later come to Python as well. And some people would say that the stack on the left side, sorry, yeah, for you it's on the left side, is a tooling of a data scientist. The tooling on the right side is the tooling of a data engineer. In some companies, it's still the case that roles are mixed and there's no clear separations and people are expected to know everything. But regardless of your job description and as people who deal with data, there is at least one thing in common. We all do exploratory data analysis with our data. And some people in deep learning community, for example, say that I don't do exploratory data analysis because I don't want to introduce my own assumptions into my model. And while there is a good room for discussions on this topic, the statement is at least inaccurate, because even if you don't plot correlations or search for outliers before you make your machine learning model, you at least do initial data analysis. You assess the quality of your data. You look for missing values. You check for descriptive statistics and that sort of thing. And this is a part of exploratory data analysis. So we all do it, but the scope may vary. You may be good to go with just the basics of assessing the quality, or you may want to go deeper and search for patterns. And you may want to use just the non-visual techniques, just get the numbers on statistics, or you may want to plot your data and try to understand what's going on in there. And exploratory data analysis, to me, feels a little bit like exciting detective adventure. It's interactive and iterative. With every step, you learn more and more. It's highly experimental. You have a lot of trial and error. You tend to start with simple things and then increase complexity as you go. And ideally, you would like to use all of the data. And if your data fits in memory, then you can go ahead and use pandas or R or what have you. If not, you can go ahead and use Spark and distributed system. Or you can, for example, try to do sampling and get a sample of your data that fits in the memory. But my problem with that is that sampling techniques are hard, and you want to make sure that your sample is representative of the distribution of your data. You want to make and you want to make sure that outliers don't throw your samples off. And the more dimensions your data has, the harder it is to get that sample right. And to me personally, it's easier to use Spark for visual data analysis than trying to get that sample right. And using all the data has advantages that, well, there is no unknown data in my analysis. And Spark ticks all the boxes. You can use all the data. It has interactive environments like Zeppelin, or you can use Jupyter as your notebook as well. It allows for a lot of experiments. It has various APIs. You can work with RDDs directly. You can use Spark data frame API if your data has structure. You can use Spark SQL. You can use your favorite programming language. You can go with Python or Java or Scala. I use Zeppelin notebooks because I like interactive environment. Zeppelin notebooks provide really cool built-in visualization capabilities, and they can plot your data. But unfortunately, as a code editor, they're not ideal. And there is some very, very, very basic code completion if you can find it. There is not much intelligence in there. And this matters in Spark specifically because a Spark job can run minutes, hours, sometimes days. And if you have a typo in your method name, it's going to crash at some point, and you've just wasted hours. And even simplest IDEs can find this sort of errors. On the other hand, we have IntelliJ IDEA, which has a really nice Scala plugin that can do code completion and code analysis, but it doesn't do plots, and you don't have this interactive environment. So today, I'm going to be doing this exploratory data analysis, and I'm going to be using IntelliJ IDEA with a new plugin. And you can say to your friends that this is, you saw it here first, because we haven't released it yet. So if it crashes during the demo, wish me luck. So this is a plugin that allows you to work on Zeppelin notebooks from IntelliJ IDEA and leverage code inspections, code completion, and that sort of thing. So now it's time for the demo. Here's the setup for this detective adventure. I've gone full meta, so I'm going to use IntelliJ IDEA to dig through IntelliJ IDEA code as a repository, and it's going to be as a text file which weighs 1.16 gigabytes, and we're going to have Spark, Zeppelin, IntelliJ IDEA, and 2 plugins. All right, I'm going to switch to IntelliJ IDEA now. OK, so this is IntelliJ IDEA. Let me know if I should increase font. Oh, do you see it? Ooh. Oh. All right. Who's is there an other cable that I can pull? Right. Okay. Display. Wait, no. Sorry about that. All right, it should work. Perfect. Sorry about that. OK. You can see that perfect. So if I go to IntelliJ IDEA and go to plugins, you can see that I have Scala plugin installed and Big Data Tools plugin installed here. That's the only difference from the regular IntelliJ IDEA. Once I have a Big Data plugin installed, I can set up different connections to remote file system or Zeppelin, Hadoop, Spark monitoring. In this case, my Zeppelin is on localhost, and my just going to test connection. OK, this is fine. Perfect. All right, so I have a notebook with code in it already, but let's go rogue. Let's start doing things from scratch. OK, so this is a Zeppelin notebook open in IntelliJ IDEA. So we're going to import the data into an RDD. And since it's a Zeppelin notebook, Spark context is already created by its Zeppelin interpreter. Too small. Better? OK, perfect. So we already have Spark context, and I know that it's a text file. So I'm just going to copy-paste the path to it. And we're going to create an RDD. And the first thing that I would like to do is to check how many lines of code is in IntelliJ IDEA repository. I can do it with a count method. And we're going to run it. One cool thing about Spark is that while it's running, I can take a sip of water. Even bigger? That's fine? All right. During the demo, we decided to go even slower than usually. Yeah, that Zeppelin is started locally. All right. Well, this is fun. And didn't work. I'll give it another couple of seconds, and if it doesn't work, I'm going to switch to the notebook that I pre-run, because troubleshooting this right now is going to take a bit of time. And we already had to fix the font and fix the... All right. All right, I'll be doing it like this then, and I can... So what we can do, no. No, in Scala, it doesn't matter in this case. This specifically doesn't matter for Scala. All right, so so we have 8 million and more lines of code in IntelliJ IDEA repository. The next thing I would like to do is take a few lines and to preview what they look like. For this, we can say rdd.take, take, let's say, 5 or 3 or 10 of them. And for each, we're going to print that line. And already I can see that there is some structure. It's not just the code. Well, I know because that's how I made this data set. So we have the path to the file. We have the line number. We have the number of lines in that file. And we have the number of bytes this file takes, and then the code on that line. So I want to convert this RDD into a data frame, into a Spark data frame. And the reason is I want to leverage this structure. And having a data frame will allow me to use SQL syntax and run queries on it. And then another thing is that when Spark knows about structure and data frames have a known schema, it can take a lot of optimizations. It can make a lot of optimizations under the hood, so I don't have to think about it. And when you're working with an RDD, you have to think about the optimizations. So there are many ways to convert this RDD into a data frame. I prefer to use case classes. So I define Scala case class with the constructor parameters, the information that I want to extract from there. And there's going to be a file path, an extension, the line number, number of lines, number of bytes, and the text of the code. This function is simply taking the string, extracting those chunks of information, and creating an instance of a case class and mapping those chunks of information into parameters. And then I just can create a new RDD, say rdd.map, use that mapping function. The reason I do it like this is because now creating a data frame is as easy as saying rdd.toDF. And now I can preview this data frame with a show method, and it gets pretty printed as a table. And I didn't have to explicitly specify schema, because once you have case classes, you can get the schema, Spark can infer the schema automatically for you from the case classes. So this is what we wanted, this is what we got. Now, once I have the data frame, I can do a lot of things simpler that it would be with an RDD. For example, I can decide to work with just one column and do something with it. For example, I'm going to just show a bunch of lines. And then I can do something similar to Boolean masking in pandas, where you specify a condition and you return only those records that match this condition. For example, I want to take only those records where the line number is 20. I'm going to see 5 of them. Now, I have extension here that I extracted from the file path, and I would like to count how many different types of files are there. And for that, in pandas, I would do value counts on the column, but for data frame, it is a little bit different. So you can do group by extension, and then you'll do a count, and then you can show the result. This was my chance normally to take another sip of water, but fortunately, the gods of them were not with me today. So we have 7.5 million lines of code in Java and 700,000 approximately lines of code in Kotlin. Now, if we wanted to do the same thing but for files, we could do this in a number of ways. For example, we can create a unique files data frame, which will be a version of original data frame. We'll just leave only those columns which are going to be the same within a file. So file path, extension, number of lines, number of bytes, drop duplicates, and then we can do the same thing and get the result. 76,000 files in Java, 6,500 files in Kotlin. Now let's zoom in on the Java files only. When we have, so to limit to Java files only, we can say unique files where extension equals Java, and where is doing essentially the same thing as filter, depending on your background. If you're coming from Scala world, filter might be more familiar. If you're more familiar with SQL, where seems more natural. And then if we have numerical columns in a Spark data frame, we can get descriptive statistics for them. So we need to use describe method and let it know which columns are numerical. In this case, it's number of lines, number of bytes. And then we can see that for Java files in IntelliJ IDEA repository, we have an average of almost 100 lines of code per file. Standard deviation is, well, I would say through the roof. It's all over the place. And the largest file is 30,451 lines of code. That's enormous. For data frames, you also have a bunch of statistical functions that you can use out of the box. For example, we can look if there's any correlation between number of lines and number of bytes. And for that, we need to use .stat.core. It's going to and let it know between which numerical columns we want to calculate the correlation. And in this case, I'm taking number of lines and number of bytes. And it's going to return Pearson correlation coefficient for these 0.77. Of course, this depends also on the number of, not only on the length of those lines in those files, and it could be an interesting thing to explore further to see maybe in some modules the lines are shorter, or maybe there is some people with a certain style of programming, and maybe there is some other dependencies here. What else you can get from .stat? From .stat, you can get approximate quantile method. Calculating quantiles on distributed data set is very expensive because you need to sort the data. And that's why in Spark, I think starting with version 2.0, but I may be mistaken on this one, they have the approximate quantile algorithm implementation originating from streaming databases community, where you can set, well, for which numerical column you want these quantiles to be calculated, which are those quantiles, and the relative error that you want. So here I can say I'm okay with 5% relative error, and the higher the error you set here, the faster it's going to run. If you set it to 0, you're going to get exact numbers. And here I run it with the exact numbers, but on Java files only, so I only have 76-something thousand records. So I wouldn't do this on my laptop on the full 8 million lines, because that would probably crash it. An interesting thing that we see here, that half of the Java files in IntelliJ IDEA repository are under 39 lines of code, and then there's 1% that's over 881 lines of code. Another potentially interesting avenue for exploration. We can see what those files are that are larger than 20,000 lines. We can do, again, filter with the condition. We can use number of lines greater than 20,000. We can limit to just the path. And when showing long lines, you can use truncate equals false. Otherwise, it's going to cut off and show only tiny part of it. And when we do this, we see that the two largest files are actually located in test data. And one of them is called long class Java. So perhaps if you were exploring this data set and looking for patterns and coding styles or something, we would want to exclude the test data, because a lot of it is just gibberish used for different edge case testing and that sort of thing. So so here I exclude the test data. I exclude all the paths where test data is where there's test data, and I do I get the descriptive statistic again, and this time nearly 20,000 files were in the test data. That's a lot of test data, actually. And the standard deviation is still pretty high, and the largest file is still pretty high, but the mean got higher. We can also visualize the data using either Taplane or IntelliJ IDEA with Taplane. So, for example, if I wanted to plot the distribution of the file sizes in this data set, what I could do is create a lines count data frame, which is going to be grouped by number of lines, then count and order by number of lines. And the way it works with Taplane is that it can visualize SQL queries. So we want to give it a query, but before we can do that, we need to let Spark know. We need to create SQL temporary view to a data frame and give it a name, and that name we will be able to use from the from statement. So that's what we do here. We take this data frame, lines count, we create or replace temporary view, call it lines, and then we can just tell Taplane that this is going to be an SQL cell, and we can use plain alt SQL. Select everything from lines, and we get a nice chart like that. And IntelliJ IDEA in this case automatically picks the chart that is going to be the most appropriate. There is nothing surprising in this chart. It looks what we would expect from the descriptive statistics, except maybe this part. where it goes up, 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 and then it drops, and then goes back up. So perhaps we would want to explore what's going on here. Why does it go down? And maybe find something interesting. Now, I did all of this just for the Java files. Let's do the Kotlin part for the comparison. And it's going to be a little bit shorter because I already went through the same steps with Java files. So I just condensed this for Kotlin. So we're going to take, again, the unique files where extension is Kotlin, and remove the files that contains test data in the path, and then call the describe method for numerical columns, number of lines, and number of bytes. And what we see here is still the mean is around 100-something lines. Quite high standard deviation, but not as high as for Java files. So this is different in Kotlin. And the maximum length of file is about 3.5 times smaller than in Java. If we calculate approximate quantiles for Kotlin files and take the same 0.5, 0.9, and 99% quantiles, we get a similar picture for the 90% and for the 99% we get, but for 50%, it's very different. So for Java files, if you remember, half of the files were under 39 lines of code. In this case, we see that half of the files is under 64 lines of code. So so there is a difference there. We can also plot, we can also take the number of lines and number of bytes and plot them against each other. And again, for that, we're going to just take these columns, create a temporary SQL view to them, and use regular plain SQL to query that data. We're just going to take everything from this data frame. And again, it can automatically choose an appropriate plot for this data. So now we can see that we have a number of bytes on one axis, and we have number of lines, and on one axis, number of bytes on the other one. And we can explore it in more details, or perhaps save it into a PNG file and send it to someone who wants to explore it further. We haven't touched on the code itself. So for the moment, I've been playing with the number of lines, number of bytes. If we want to look in the text itself, we can start with the simple things. For example, we can calculate the average number of imports per file in Kotlin and in Java files. We can do this with very simple methods, like we're going to limit our Kotlin counted imports to where extension is Kotlin and text. So the code on that line starts with import, and file path does not contain test data. Then group by file path and count them up. And then when we use select, in the select we can also use aggregators. We can ask for an average or for a sum in this case. And with essentially 2 lines of code, we get the answer. And the answer is 2.9 imports per Kotlin file on average. Doing the same for Java, we see that the number of imports per file on average is 10.7, so a little bit bigger. We can create we can create these data frames as views for the original RDD in different shapes and whatever, depending on what we want to explore. For example, I created this data frame just by extracting this, splitting this original string into different chunks of information. And I could be interested into calculating, for example, different imports, how many static imports there are, how many regular imports there are. And I can go around another way. So for example, I'm going to create an imports RDD using the original RDD, and by just filtering taking only the lines that starts with import and are not in test data. And then I can map it differently to create a different data frame. For example, I will just take the text part, and I'm going to map it to key value pairs, where the key will be a tuple of the import name. And there's a bunch of if statements because there is different ways of importing things in Kotlin and Java. You can import something, you can import something as something else, or you can import static something. So essentially, there's 3 ways it can go. So there's the name of the import, whether it's static or not, and then we have the value of 1. So then we can do reduce by key to count them up. We can map them into unrolled version of it and convert to data frame. In this case, I need to explicitly specify the schema, because this is just a regular RDD. There's no case classes, so I have to be explicit about what my schema is. And once I do that, I get a different kind of data frame to which I again can create an SQL view. And for example, find out what are the top 10 static imports. And I can continue with more complex queries. All right. So we've seen a bunch of stuff here. So like that you can do. You can map and reduce by key and work with your RDD directly. And then you can convert it to appropriate data frames, so you can leverage all those statistical functions that you have. Where is it? You can use this, for the descriptive statistic or more complex statistical information, you can, if you're running SQL queries, you can plot your data in a Zeppelin notebook or in IntelliJ IDEA, and you can visually explore it like that. There's a lot of potential of what you can do here, and it all depends on ultimately on what exactly you're trying to do with the data, what the question is, what you're trying to achieve. Are you preparing for some machine learning model, or are you just looking for inspiration in your data and deciding where to go next with it? It all depends on your business problem and your data and what you want to do. But like in some TV shows, they give a disclaimer, like, do not try this at home. I want to urge you to do the opposite and go ahead and try this at home. And if you want to do that, let me switch back to my slides. If you want to do that, I've shared the notebook on GitHub, and I'm going to be tweeting this again later. And eventually, this plugin is going to be released. And if you want to play with that, there's a link to sign up for the preview. And right, you don't need the plugin to run the notebook. You can just use Zeppelin. You can install Zeppelin locally. It's an open source project, so that would be enough. And thank you for your time.
Thank you very much, Maria. This is a certificate of appreciation. And I think we still have time for questions.
I think
No?
Have a question and answer right now?
They don't?